Already we had discussed on chapter 9. The title of chapter 9 was inner product spaces and Hilbert spaces. In this chapter we have learned some properties of inner product spaces and also we have learned some basic properties of orthogonal vectors and orthonormal vectors. Also we shall learn on annihilator of a subset and orthogonal complement of a subset in an inner product spaces. Already we have acquainted with some basic properties of inner product spaces. Today we shall discuss on complete orthonormal set. Any orthonormal set can be extended to a complete orthonormal set of vectors in an inner product space. Also we shall learn on a topic that any set of independent vectors can be extended to a complete orthonormal set, and this is done by a Gram-Schmidt orthogonalization process. Now we are discussing on module 4 of chapter 9. The title of module 4 is some results on Hilbert spaces. Now let us take a theorem. The annihilator of a subset and the orthogonal complement of a subset coincide in a Hilbert space. The annihilator of a subset means the collection of all linear functionals which are always bounded such that inner product x comma x dash equal to 0, where x dash is taken from set of all bounded linear functionals. So the proof goes below. Let H be a Hilbert space and let S is a subset of H. We have S perp is equal to collection of all such elements while belonging to capital H such that inner product x comma y is equal to 0 for all x belonging to capital S. Now by Ridge representation theorem, note that for every f belonging to H star, that is the conjugate space of capital H, there exists a unique element y belonging to capital H such that fx is equal to inner product x comma y for all x belongs to capital H. So the correspondence f to y and the vice versa from y to f have appeared, and we get norm of f is equal to norm of y. Thus S over superscript A is equal to collection of all functionals f belonging to H dash such that fx equal to 0 for all x belongs to capital S. That means the collection of all y belonging to capital H such that inner product x comma y is equal to 0 for all x belongs to capital S, which is equal to S perp, implying that the annihilator of S and the complement of S coincide in a Hilbert space capital H. Now let us take a theorem. Let X be a separable inner product space and let M be an orthonormal set in X, then M is countable. X be a separable inner product space means there exists a countable set which is everywhere dense in X. Now let us take a proof of this theorem. Let x comma y belongs to capital M such that x is different from y. So norm of x equal to 1, which is equal to norm of y, and inner product x comma y is equal to 0. Now norm of x minus y whole square is equal to inner product x minus y comma x minus y, which is equal to norm of x square plus norm of y square. We have used the inner product relation, but inner product x comma y is equal to 0. Thus norm of x square plus norm of y square is equal to 2. That means norm of x minus y whole square equal to 2. That means norm of x minus y is equal to root 2. As x is separable, there exists a countable set A y1, y2 dot 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 yn in X, which is everywhere dense in capital X. Let u comma v belongs to M, which is again a subset of X such that u is not equal to v. Let epsilon greater than 0 be arbitrary. So we can find yn and ym in A such that norm of u minus yn strictly less than root over 2 by 3 and norm of v minus ym strictly less than root over 2 by 3. Now norm of u minus v less or equals to norm of u minus yn plus norm of yn minus ym plus norm of ym minus v. It is used by triangle inequality of norm axiom 3. which is again less than 2 root 2 by 3 plus norm of yn minus ym. Therefore, root 2 is strictly less than 2 root 2 by 3 plus norm of yn minus ym, which on simple calculation we get norm of yn minus ym is strictly greater than root 2 by 3, which implies that yn is not equal to ym. So, we see that u not equal to v implies yn not equal to ym. Thus, the mapping M to A defined by u to yn is 1-1 correspondence. So, M is countable. Now, let us take another theorem which is very important theorem in Hilbert space. Let X be an inner product space, then there exists a complete orthonormal set in X, and any orthonormal set in X can be extended to a complete orthonormal set in capital X. First, we shall prove 2. If we can prove 2, then automatically 1 follows. So, we shall now prove 2. Let X belongs to capital X such that X is not equal to 0 vector. Then the singleton set X over norm of X is an orthonormal set. Thus, in X an orthonormal set always exists. Let E be an orthonormal set in X. Take S equal to collection of all sets A alpha, where alpha belongs to delta, delta being the indexing set, and S be a family of orthonormal set containing E. Clearly, S is non-empty. We now define a partial order relation with respect to set inclusion relation on S. Then S is a partially ordered set. Let tau be a family of all such sets B alpha, where alpha belongs to delta, be a totally ordered set in S. Now, E is a subset of B alpha for all alpha belongs to indexing set delta. We shall now show that union of B alpha, where union is taken over alpha belongs to delta, is an upper bound for tau. Now, union of B alpha, where alpha belongs to delta, belongs to S. Let X comma y, where X not equal to y, belongs to union of all B alpha, where alpha belongs to delta. This implies that X belongs to B alpha for some alpha belongs to delta, and y belongs to B beta for some beta belongs to delta. As tau is totally ordered, either B alpha is a subset of B beta or B beta is a subset of B alpha. Without loss of generality, let B alpha is a subset of B beta. So, X belongs to B alpha implies X belongs to B beta. Also, norm of X equal to 1 and norm of y equal to 1, since B beta is an orthonormal set in capital X. Since X comma y belongs to B beta, we have inner product X comma y is equal to 0. So, union of B alpha, where alpha belongs to delta, is an orthonormal set in capital X containing E, and each B alpha belongs to union of B alpha, where alpha belongs to delta. So, union of B alpha, where alpha belongs to delta, is an upper bound for tau in S. So, S is inductively ordered. So, by Jones lemma, S has a maximal element, say capital A, which is a complete orthonormal set in X containing E. If not, there exists an orthonormal set containing E and also containing A properly. This will contradict the maximality of A, thus 2 is proved. Now, let us take a theorem. Let capital X be an inner product space, and let y1, y2 dot dot yn dot 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 be a set of linearly independent vectors in capital X. Then there exists an orthonormal set x1, x2 dot dot xn dot 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 belongs to capital X such that box collection of elements y1, y2 dot dot yn is equal to box collection of elements x1, x2, xn, where n is not fixed. The proof follows by principle of mathematical induction. For n is equal to 1, take y1 is a non-zero element belonging to capital X. Take x1 is equal to y1 by norm of y1. So, norm of x1 is equal to 1. So, box singleton set y1 is equal to box singleton set x1 by simple calculation, where norm of y1 is equal to alpha. Let us assume that the result is true for n minus 1 elements, that is box collection of elements y1, y2 up to yn minus 1 is equal to box collection of elements x1, x2 up to xn minus 1. Let W equal to yn minus sigma k equal to 1 to n minus 1 inner product yn comma xk into xk. Thus, for 1 less or equals to j less or equals to n minus 1, we have inner product W comma xj equal to inner product yn minus sigma k equal to 1 to n minus 1 inner product yn comma xk into xk comma xj, which is equal to inner product yn comma xj minus inner product sigma k equal to 1 to n minus 1 inner product yn comma xk into xk comma xj, which is equal to inner product yn comma xj minus inner product yn comma xj, which is equal to 0. So, inner product W comma xj equal to 0 for all j lies between 1 to n minus 1. This implies W is perpendicular to xj for all j lies between 1 to n minus 1. Now, W not equal to 0, otherwise the set y1, y2 up to yn would be linearly dependent. Let us take xn is equal to W by norm of W. So, norm of xn equal to 1. Therefore, xn equal to 1 by norm of W into yn minus sigma k equal to 1 to n minus 1 inner product yn comma xk into xk, which is equal to say beta into yn minus sigma k equal to 1 to n minus 1 inner product yn comma xk into xk, where beta equal to 1 by norm of W. It is easy to verify that box collection of elements y1, y2, yn is equal to box collection of all elements x1, x2 up to xn. Thus, the result follows by principle of mathematical induction. In this context, let us take a remark. Let X be a finite dimensional inner product space, then there exists a basis of capital X formed by a set of orthonormal vectors in capital X. Now, let us take a theorem. Let S be a finite dimensional subspace of a Hilbert space capital X, then for X belonging to capital X, there exists a unique vector y0 belongs to capital S such that norm of x minus y naught is less or equals to norm of x minus y for all y belongs to capital S. Let dimension of S is equal to n. So, there exist a n numbers of orthonormal vectors y1, y2 up to yn in S, which forms a basis for capital S. Take y naught is equal to inner product x comma y1 into y1 plus inner product x comma y2 into y2 plus dot 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 plus inner product x comma yn into yn. So, y naught belonging to capital S. Now, inner product y naught comma y1 is equal to inner product x comma y1, which implies that inner product x minus y naught comma y1 is equal to 0. Thus, inner product x minus y naught comma yj is equal to 0 for all j lies between 1 to n. Therefore, x minus y naught is perpendicular to S as collection of elements y1, y2 up to yn belonging to capital S. So, by earlier theorem, norm of x minus alpha 1 y1 plus alpha 2 y2 plus dot 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 plus alpha n yn attains its minimum value at alpha 1 alpha 2 dot dot alpha n belonging to Cn whenever inner product x comma yk is equal to alpha k, k is equal to 1 2 up to n. Thus, y naught is the required vector in S such that norm of x minus y naught less or equals to norm of x minus y for all y belonging to capital S whenever y naught is equal to inner product x comma y1 into y1 plus inner product x comma y2 into y2 plus dot 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 plus inner product x comma yn into yn. If possible, let y naught is equal to beta 1 y1 plus beta 2 y2 plus dot 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 plus beta n yn be another representation of y naught as collection of elements y1, y2 up to yn is linearly independent. We have beta I is equal to inner product x comma yi, I equal to 1 2 up to n. Hence, alpha I equal to beta I for I equal to 1 2 up to n. Thus, y naught belonging to capital S is unique. Now, we are going to discuss some further properties on Hilbert spaces. The properties, namely, if S be a complete subspace of an inner product space, then there always exists a vector which is unique belonging to capital S such that norm of x minus y naught is less or equals to norm of x minus y for all y belonging to capital S, and x minus y naught is perpendicular to S. And from this we shall conclude that there always exists a unique vector in capital S of smallest norm. In the context of earlier theorem, we get another theorem. Let capital S be a complete subspace of an inner product space capital X, and if x belongs to capital X be any vector, then there exists a unique vector y naught belonging to capital S such that norm of x minus y naught is less or equals to norm of x minus y for all y belonging to capital S, and number 2, x minus y naught is perpendicular to capital S. Now, in this context, we get another theorem. Let S be a complete convex subset of an Hilbert space capital X. In earlier theorem, we have stated S be a subspace which is a complete. Here, instead of the subspace, we take convex subset. So, thus we have taken S be a complete convex subset of an Hilbert space capital X, and let x belongs to capital X be any vector, then there exists a unique vector y naught belonging to capital S such that norm of x minus y naught is less or equals to norm of x minus y for all y belonging to capital S. The proof looks like this. Let delta equal to infimum of norm of x minus y, where y is taken from S. So, there exists a sequence of vectors yn belonging to capital S such that norm of x minus yn goes to delta as n tends to infinity. Now, for any n comma m belongs to natural numbers set n, we get norm of ym minus x plus norm of yn minus x whole square plus norm of ym minus x minus yn minus x whole square equal to 2 into norm of ym minus x whole square plus norm of yn minus x whole square by parallelogram law. So, norm of ym plus yn minus 2x whole square plus norm of ym minus yn whole square equal to 2 times norm of ym minus x whole square plus norm of yn minus x whole square, which implies that 4 into norm of yn plus ym by 2 minus x whole square plus norm of ym minus yn square equal to 2 into norm of ym minus x whole square plus norm of yn minus x square, which implies that norm of ym minus yn square equal to 2 times norm of yn minus x square plus norm of ym minus x whole square minus 4 into norm of ym plus yn by 2 minus x square. This is known as equation number 1. As ym comma yn belonging to capital S, ym plus yn by 2 belongs to capital S as S is convex. So, norm of x minus ym plus yn by 2 is greater or equals to delta. So, from equation number 1 we get norm of ym minus yn square is less or equals to 2 times norm of ym minus x square plus norm of yn minus x square minus 4 delta square, which gives 2 delta square plus 2 delta square minus 4 delta square, and which goes to 0 as n comma m tends to infinity. So, norm of ym minus yn tends to 0 as m comma n tends to infinity. So, yn is a Cauchy sequence in capital S. As S is complete, we get yn goes to y naught which belongs to capital S. So, for any x belongs to capital X, yn minus x goes to y naught minus x as n tends to infinity, and hence norm of yn minus x goes to norm of y naught minus x as n tends to infinity. Again, norm of yn minus x goes to delta as n tends to infinity. So, delta equal to norm of y naught minus x. So, norm of y naught minus x is less or equals to norm of x minus y for all y belongs to capital S. We shall now show that y naught is unique. If possible, let y naught is not unique. So,
there exists an element Z0 which is not equal to Y0 belongs to capital S such that norm of x minus Z0 is less or equals to norm of x minus y for all y belongs to capital S, where norm of x minus Z0 equal to delta. Now, norm Y0 minus x plus x minus Z0 whole square plus norm Y0 minus x minus x minus Z0 whole square is equal to 2 times norm of Y0 minus x square plus norm Z0 minus x square, which implies that norm Y0 minus Z0 square plus norm Y0 plus Z0 minus 2x square equal to 2 into 2 delta square equal to 4 delta square. So, norm Y0 minus Z0 square plus 4 times norm Y0 plus Z0 by 2 minus x square equal to 4 delta square. So, norm of Y0 minus Z0 square equal to 4 delta square minus 4 times norm Y0 plus Z0 by 2 minus x square, but Y0 plus Z0 belongs to 2 belongs to capital S as S is convex. So, norm x minus Y0 plus Z0 by 2 is greater or equals to delta. Thus, from equation number 2 we have norm Y0 minus Z0 square less or equals to 0, and hence Y0 minus Z0 equal to 0, implying that Y0 equal to Z0. Thus, Y0 belongs to capital S is unique. Now, we get another theorem. Let capital S be a complete subspace of a Hilbert space capital X. Let X belongs to capital X, then there exists a unique vector Y0 belongs to capital S such that norm x minus Y0 less or equals to norm x minus y for all y belongs to capital S. And number 2, x minus Y0 is perpendicular to capital S. As capital S is a linear subspace of capital X, it follows that S is convex. So, one follows from the earlier theorem. Now, for the proof of 2, let Z equal to x minus Y0, where Y0 belongs to capital S. Let y be any vector in capital S such that norm of y equal to 1. Let lambda be any scalar. Now, norm z minus lambda y square is equal to inner product z minus lambda y comma z minus lambda y, which is equal to inner product z comma z minus lambda times inner product y comma z minus lambda bar into inner product z comma y plus modulus of lambda square into inner product y comma y, which is again equals to norm z square minus lambda times inner product y comma z minus lambda bar into inner product z comma y plus modulus of lambda square as norm of y equal to 1, which is equal to, on simple calculation, norm of z square minus modulus of inner product z comma y whole square plus modulus of inner product z comma y minus lambda square. Take lambda not equal to inner product z comma y. So, norm z minus lambda not y square equal to norm z square minus modulus of inner product z comma y square. Now, z minus lambda not y equal to x minus y naught minus lambda not y, as z is equal to x minus y naught is assumed. So, which is equal to x minus y naught plus lambda not y, but y naught plus lambda not y belongs to capital S. So, norm of x minus y naught is less or equals to norm x minus y naught plus lambda not y, which is equal to norm z minus lambda not y, because z equal to x minus y naught. So, norm z is less or equals to norm z minus lambda not y. Therefore, norm z square is less or equals to norm z minus lambda not y square is equal to norm z square minus modulus of inner product z comma y square. Thus, modulus of inner product z comma y square is less or equals to 0, which implies that inner product z comma y equal to 0. Hence, z is perpendicular to y. So, x minus y naught is perpendicular to s, and thus the proof of 2 follows.
In this module, we have learnt some additional properties on inner product spaces, namely the existence of a complete orthonormal set of vectors in an inner product space. Also, we have learned the existence of a unique vector of smallest norm. With this, we now come to an end of this module 4.